Oh, you can't do that. Well, look, there it is. The bottom line. You have no idea what this is yet, but look at this. Going to start at the end. It's called backwards design, folks. It means you start with the end goal in mind. Here's the bottom line. We need to understand that all circles are similar. We need to understand that. Yeah, we do. Yeah, that's kind of a good thing. So if all circles are similar, we then can go from there backwards. Similar. Right there. Good old similar symbol. That means that all the arc lengths and the sector areas have something going on there. Something proportional. But really, this is mostly about the arc lengths. So if you compare two circles and you compare their radii, look at that, I didn't say radiuses, folks. I know you like the radiuses comment, but hey, that means that if you compare radius 1 here to radius 2 over here, there's something going on there. It's a scale factor. The good old K in the middle. Those are single dimensions. That's what that means, single dimensions. So the radius are proportional. They're all multiplied by that K or that scale factor. San Francisco, if you remember that one. And then also the arc lengths. If you make a couple of radii, you say, oh, well, there's an arc, and there's an arc. As long as the angles are the same, then those arcs are also going to be proportional because they're lengths, single dimensions, one-dimensional values. They go by a scale factor. And if you go for areas, just a reminder that area actually goes up by a value of k squared. You remember that from way back in unit whatever? K squared. But this is mostly about the arc length. So that's the end goal, is to understand these things, that the radius and the arc length of a dilated circle is directly proportional by a k value or a scale factor. And this is because they are one-dimensional values. There you go. That's the end of the lesson in 1 minute and 56 seconds. No, it's not. Let's go back to the beginning. Back to the top. Where's the top? Oh, top is right here. Sorry, I went to the bottom again. Here's the top. All right, taking a look at a cell phone and a iPad, and they're charging. There's progress being made here. It's one of those fun things. But if you take a look at you actually draw on here a couple radii and a center, you'll notice that they have the same central angle. So that's kind of key. Equal. Oops, that's not equal. That's equal. Central angles. Angles. There we go, the angle symbol. And that they also have this kind of idea that the radius of one and the radius of the other one are proportional. There's some scale factor there. We just don't know what it is. And the arc lengths are also proportional. We just don't know what to multiply them by. You can use scale factor, you can use K factor, you can call it Fred, I don't care. Fred factor, there you go. The Fred factor. Fred Flintstone factor. Okay, too much sugar. Here we go. Let's take it out what it looks like with numbers. So here we're going to be serious now. Can we be serious? Yes, we can. So, two circles. We're just going to say this one has a radius of 1. And if they have a scale factor of 3, that means this one will be 3. So it's just a easy, let's keep the numbers simple. So the circumference over here of circle 1, the little guy, would be 2 pi. That would be pi times the diameter. If you remember, if you've been following the conversation here, we're using pi times the diameter. And then that's a fraction. Now, I know some of you are going to be like, well, God, I want to use my calculator. I want to use 90 over 360. Don't. Why bother? You don't need to. It's 1/4. That's 1/4 of the total circumference. So there's our circumference. 1 plus 1 is 2 pi. So that means the actual arc length, if you will, arc length is going to be 2/4. That's 1/2, folks. 1/2 pi. I'm going to write it just like that. And then when I go over here, I'm going to go with this circle, I'm going to say that that's going to be a diameter of 6. So the circumference is going to be 6 pi. And the fraction of the circle is still the same. It's still 1/4. That's what it is. It's 1/4. So the arc length is 1/4 of the total circumference. Now you'll notice that 6 times 1 divided by 4 is 6/4. We know that as 3/2. And there's still a pi there. So we stop and compare. We stop and take a look. Take a look. Please do. It's a good thing for you. 1/2, 3/2. Well, what's 1/2 to get 3/2? That's a scale factor. That's times 3. So everything was times 3. And I know this isn't part of the lesson, but we talked about it in class anyway, that if we look at the areas, the sector areas, you could actually get this over here and say that's times k squared, because the areas are by squared units because you're multiplying by k twice. But it's this idea that these circles are similar. They just are. There's no doubting about it. And the radius is proportional by a scale factor of 3. K of 3. And the arc length is also proportional by a scale factor of 3. So that's the big deal. That is the big deal. And we can do this over and over again and no, really, wait a minute. How dogs cry for help. Damn pop-ups. Go away. How dogs cry for help. I don't want to hear dogs cry for help. That's not nice. It's Friday. Okay, so let's get out of there. Go away, dogs. All right, 3. Let's do this again. What's the scale factor dilation from 3 to 9? That k value right there is 3. Okay, 3 times 3 is 9. Let's not make a mistake about that. So that, real quick, is 3. What's the length of the highlighted arc? Well, the circumference is going to be 6 pi, because that's pi times the diameter, and it's still 1/4. So in this case, this little arc right there, that little tiny arc right there, it's so small, is going to be 6/4 pi, or 3/2. So that's our little guy. Now, if we follow the rule and we say that's a scale factor of 3, this really should just be, over here, it should just be 3/2 times 3 pi, or 9/2 pi. That should be what happens. Well, let's just check it. I mean, let's verify that our theory is correct. So 9 here, that means the diameter is 18, and that's the circumference, and it's still 1/4. So you're going to get 18/4. Well, guess what? 18/4. Reduce it. Oops, that is an ugly pi there. That is an ugly pi. Let's clean that up. Okay, 18/4. That reduces down to 9/2. So check. It's true. The radius is proportional by scale factor of 3. The arc length is proportional by a scale factor of 3. The ratio of the arc length compared to the scale factor is the same thing. So we can do that over and over again. There's your summary. Pause, read, check, and we come right back to where we started, folks. Bottom line, you need to calculate sector length and arc area. We still need to do that. We can compare the arc length and its radius. What's going on there between the arc length and the radius? There's something happening there. We can compare the two. And we understand that the radius and the arc length of the dilated circles are directly proportional by that k value, or the scale factor. That's because they are one-dimensional values. And bottom line, we understand that all circles are similar. That's part of this process too. All right, you know what happens next. Kind of looks like this. Ooh, how about a baby poop green? Why not? I wonder how many people actually get this far. Huh. Make a comment if you get that far. Why not?